The organizers for the invitation, this opportunity to present this talk. So I changed the title of the lecture because this is a recent work, and I think interesting recent work that is now under completion in collaboration with Gilles Albou. So what is the subject of this work? So we have a sequence of embeddings of Lie algebras. So we have this Lie algebra G, GRT, double shuffle, and KRV. And all this is a Lie subalgebra of the Lie of xy with Ihara bracket. So what are these Lie algebras? So this is motivic. So the Lie algebra of the motivic Galois group. So this is GRT, so Grothendieck-Teichmüller. This is double shuffle Lie algebra. And this is a graded version of Kashiwara-Vergne Lie algebra. And conjecturally, they are all equal. Oh yeah. Yeah. And also, thanks to the theorem of Brown, this is free Lie algebra in a collection of generators, semi-direct product with Q. Okay. So, and this Lie algebra, the Ihara Lie algebra, has a depth filtration. So, and depth filtration says that field E, Fi, of this Lie xy is, let us say, the words is spanned by words with more than I letters Y. And this is a filtration, Lie algebra filtration, so it induces the filtration of all these Lie algebras, and therefore we have associated graded for this depth filtration. The associated graded Lie algebra.
So the double shuffle is somehow the dual of the zeta functions, is that right? Of usual
yeah.
Dual vector space. Yeah. So therefore, because the usual filtration there is at most I, not at least I. Depth is less than or equal to something. It's a decreasing filtration. It's a dual. Because it's the dual. It's very confusing. Okay.
So you have this sequence of inclusions. And this associated graded of Lie is Lie itself. So here it's in fact also a gradation. Okay, and then the question is, so here I should write at least the grady of ds. Depth filtration. Okay, and here, so in fact we have information about this associated graded vector spaces. So here you have so you have the BK conjecture. So BK conjecture, so Brodeur-Kramer conjecture. So it gives a precise formula for the dimensions. So predicts the dimensions of each graded dimension. So let's say of each I d of G. So this is
comma K. You need two indices, otherwise the dimension.
Yeah, we said the dimension with this dimension means a series here.
Oh, it's an underlined dimension.
Underlined dimension. Okay. So the prediction is as follows. So you say that dim of gre 1 d of G should be t3 over 1 minus t squared. dim of gr 2d of g is t8 1 minus t square minus t6, and dim of gr 2d 3 of g is t11 1 minus t4 1 minus t6. Okay, and in fact this is known to be true. So and in fact it is known to be true up to degree 3. Thanks to so, and how is it known? So in degree 1 it is well known, let us say. In degree 2 this follows from work of people, so I think.
Do you mean G or double shuffle?
Well, it doesn't matter.
Well,
Since
it's known.
conjectural.
I know, but when you say it's known for double shuffle.
Oh, I see.
It's known for
certainly known for
double
It's
shuffle.
known for double shuffle, but I'm not sure it's known for G itself.
It's conjecturally known.
Yeah, it's not.
Conjecture.
Okay, let us say, so
It would be safer to put double shuffle.
let us put the double shuffle, okay? For degree, so so let us say DS version. So degree 2, I think there are several people who should mention, so people who did modular forms, etc. So Lila Schneps. So many people, Ekal maybe. Degree 3, it is hard and one has to rely on results on Goncharov. And in fact, the way Goncharov does this, he connects it with the cohomology of GL3. With values in powers of C3.
I'm not sure he does double shuffle. I mean, he does some motivic thing. I'm not sure he does double shuffle. So I once did double shuffle with the inequality, so that the dimensions are greater than or equal or less than or equal. And that was going to be in the paper with the Hagen Kaneko. I couldn't find my notes, so I could never find the proof. But we wrote that we knew how to prove it, right? I knew how to prove it, and then the referee, who was obviously Goncharov, said that he had proved it, but he had proved it for a different space. So he proved it for the motivic. And I think not for the, I'm not sure it's actually physical.
Because in his paper, so when I read his paper, my impression was that it was a co-algebra which was apparently dual to double shuffle. And then Leila...
No, but he also proved it for degree, for depth 2, also proved it longer. Goncharov also proved it for depth 2 longer.
That's too is rather easy. Yeah?
I mean, I did this in 1982 or something. I think before any of these, but it doesn't matter.
Yeah, actually, Donzaghi proved it a long, long time ago.
For the two, okay.
25 years ago or something. Long before any of these, the algebras existed. So it's really easy. But 3 is not at all easy, and many other people did it.
No, I think Goncharov is for double shuffle.
So,
Dihedral, yeah, what's it called? Dihedral,
He didn't say,
yeah, the
if he was the
dihedral-
referee, he didn't, he said that it was proved by Goncharov for a slightly differently defined thing. He didn't actually claim.
so what would be your statement? That Goncharov
sure.
did what? Did the motivic case or what? I wouldn't say that. So because it's very
If I had my
explicit.
paper here with you, I could look what we wrote. And we wrote what the referee told us it doesn't matter, please go on.
Okay.
It's always happens. It's
Because
really wrong.
Leila always mentions to me that this is proof for double shuffle.
Yeah,
And
I
I think, and also my impression is that Goncharov's paper has to do with double shuffle. It would be a co-algebra dual to the double shuffle. But I've never seen a proof in print that of this statement that Goncharov's algebra is dual to double shuffle.
That
What
was
is your
exactly what
opinion?
the referee wasn't sure. He said for a slightly differently defined algebra, he proved it.
Mhm.
It surjects or something, so it proves one direction, but he wasn't sure it proved both. But it surely is true, and it's surely Goncharov. So,
Yeah.
but I'm not sure he actually formally proved it for some.
Yeah.
So
it's Goncharov, it's true, but we don't know what is true.
but we don't know that it's true by Goncharov in this case. Yeah. And he proved the essential statement for one of these. Let's go on.
Okay. So now in the okay, what in fact the strategy of proof is to prove that in the case of Goncharov is to prove that this Grothendieck string of ds is contained of what is now called linear double shuffle. So it's a space of polynomials. And
So that's also not known to be equal.
it's included, it's contained.
But it's conjecturally also equal, or not?
Now, linear double shuffle, the definition I saw in Brown, it's a space of polynomials.
Well, I mean, I defined this space, so I know it.
Yes.
But I thought this is conjecturally also
Conjecturally equal,
because
yeah.
it's true that when I talk about the referee, our paper was about linear double shuffle. So the question was whether it was for linear double shuffle. So maybe it's a question whether this is.
So it's a space of polynomials plus conditions, satisfying 4 conditions, yeah?
Yeah, that's the one that I defined. Also 25 years
Why
ago.
4 conditions?
There are the double shuffle conditions, the linear, so it's
It's 2 times the integer part of r plus 1 over 2, so r is 3, it's 4.
yeah. So you have let us say, so it's a condition of the type you have p of x1, x2, x3 plus etc. equals 0. So it's the shuffle of 1 with 2, and you have a condition
Why
of
why 2? Why is it? Why is
Only
it
two.
shuffle? Why isn't it shuffle plus shuffle?
Sorry, for wait, 3 it's only 2. You can only write 3 as 1 plus 2. 2 plus 1 is the same.
Oh, in grid depth.
It's for depth 4. There are
you have 2 conditions.
two
Okay.
conditions. Yeah, sorry. Okay. So then, then I amend what I said before. What we proved
So
was
for you,
LDS, and we proved that it was for DS, and that part is not known.
so in your case, so the linear double shuffle is the space of polynomial is a small.
That's the space I defined many years ago. This
Yeah.
is my space.
Okay.
And that was the one where I did the referee said he proved for a slightly different space. So I think you're right, that did double shuffle, and I was thinking of linear double shuffle.
Okay.
I didn't realize this is also not done.
Mhm.
Everything is conjectured the same as everything else.
LDS is what
Linear.
it can call.
Linear.
Yeah, he did it also
Yeah, yeah.
many years ago.
Many
He
years
didn't
ago.
publish it, I think, and I didn't publish it. Maybe.
Okay.
Nobody understood it.
Okay. And in general, you can do this. So it's LES3, and you can continue this. You have for higher degree. So. Okay. Now, in fact, there is a conjecture that ds is equal to, so everything is equal here. Yeah. But if we don't take this conjecture for granted, then maybe we're interested in studying the depth filtration associated with the GRT algebra itself. So the subject of the talk. So, the subject of today, to find an upper bound for d of GRT. So the main message of today is that there is such an upper bound, and it can be so we'll construct this upper bound I, and this upper bound is a space of polynomials. It can be identified with a space polynomials in I variables. So subject to condition. And so to give a few examples, when I equals 1, up I is not very interesting, so it's too big. But when I equals 2, so up I Up 2 has exactly the right size. You have d of up I is the dimension of decay. So borders claim a dimension. And for I equals 3, also.
Well, wait, there is. Well, you put in a subscript of BK. I mean, there's no space BK in the conjecture.
Yeah, the dimension. Yeah, that's right. The BK dimension, the BK series. Yeah, there is no BK space. You're right.
Yeah,
So
but there is a linearized double shuffle space, which is also polynomial. So you could just say here.
D. They say D.
But are those spaces the same?
D of t. Let's say D of t. BK2 of t. Yeah, it's a series in t. And also, and this is also true. So in fact, to prove this here, I use some Goncharov technique. In fact, so this is proved using Goncharov.
But you don't know the dimension of I in general.
No, not in general.
So you don't have an upper bound, it's an upper bound space.
It's over space.
Not an upper bound bound.
Yeah.
So is there any relation? I mean, LDS is also a space of polynomials in I variables. So is there a map between them which you can
That's a good question.
equality?
So, yeah. So in fact, I want to test this in dimension in degree in depth 4.
No,
so
but first in depth 2 and 3.
So in depth 2 and 3,
Where you know that the dimensions are correct, or the space is equal, the dimensions are the same. Because there the argument is proved, well, I'm not 100% sure for linear, but anyway, maybe proved to have the right dimension.
yeah, I
Your
think
space is proved, and they both are a space of polynomials.
in
the
those
same
cases,
degree?
yes, they are the same spaces of polynomials. Well,
The
you
actual
see,
space is the same. Just isomorphic, or, I mean, it's,
I think they are just the same. Are they? I think they should be isomorphic, but I'm not completely sure. So the dimensions are the same. So for any degree, so the impression is that they should be the same.
also, is up I in weight k, does that mean that it's a degree k minus I?
Up I, if you want, you have the x and y degree. Yeah?
Yeah, no, but I asked a specific question, just yes or no, not a picture. Up I in no, just it's yes or no. Is up I in degree k for weight k for the we have the weight filtration? Is it simply polynomials of degree k minus I? That's what it is in all the other cases. Is it the same?
Yes.
Okay.
Yeah.
So if I fix the weight and the degree, we have two spaces, polynomials of the same number of variables at the same total degree.
Yeah.
And for I equals 2 and 3, you think it's the same space?
Yeah, I think so.
Okay. I think just one thing.
Okay. So, okay, so how about depth 4?
No.
So up 4 is defined by 7 conditions. So, but of course, these 7 conditions could be reduced to less conditions. So,
But
and
Benjamin,
yeah.
you work in commutative variables, so you did not even define the.
Yes.
You will define.
I will define it. So it just explains the result. So it's defined by 7 conditions, whereas the LDS is defined, I think, by 4 conditions.
So the question is, do you see modular forms in up 4?
No, the first you said it's the same space.
Is it? Yeah. Is it the same space? So, for example, do this condition
Rather than
this system?
If your computer has somebody computed for small weight, but it's simply the same space.
Yes. This is the test that I should do.
Oh, so you haven't. So you don't even
Yeah,
conjecture
not-
if it's the same.
Yeah. Not yet.
Okay.
So
And
the
how about for 2 and 3? You didn't tell us the number of conditions.
here 4 conditions. And here 2 conditions.
Whereas double shuffle has 2 in both cases.
much to do.
No, maybe it's
No,
not
I mean,
space.
yeah.
It may just be, you know.
But you know, it's a system of conditions. I mean, it's just these conditions are the following form. So in general, in up I, up n. So up n is a subspace. So in fact, no, I shouldn't. No, this is not yet proved. So conjecturally, so up n should be a subspace of polynomials in n commutative variables, and the conditions should be of the form So you have G applied to P, and you have a coefficient depending on G, and the alpha for the number of the relations equals 0. Where G belongs to G ln Z. So you see that from one relation you get many relations. Yeah.
Well, I mean, as that stands, it's identical for a linear double shuffle.
Yeah. So the general form is this. So just to mean that the general form, the condition is the same in both cases.
The same type of condition.
The same type of condition.
So to say it a little differently, I have an ideal In in the group ring of GL and Z.
Absolutely.
And this is simply the things killed by that ideal.
Absolutely.
And you have a similar ideal for the other.
Absolutely.
So one can ask whether it's the same ideal.
Exactly.
But,
Exactly. And
but even
now,
numerically, you haven't checked that.
not yet. As I told you, so
even for weight 2, degree 2.
No, for two. You see, I didn't know the work about LDS very well, so I relied on Goncharov, so I should study your work on LDS, and that's why I didn't check this up to now, so I will.
Finite sum of that?
Yeah,
it's a
yeah,
number of
yeah.
group ring.
Finite sum. Okay.
Useful.
So. Okay. So this is it. So how this upper bound is obtained? So how to construct this upper bound? So for
Would it
this,
be possible before you want to give the actual condition in the case n equals 2? So
Yeah,
see,
can
it
find-
must be, that you must know.
yeah, it should be, if I remember,
Just so we see something.
n equals 2,
There are only two conditions. So it's-
f of is antisymmetric. And then you have f of it's some time ago, so I already forgot. I can write all the conditions.
You choose. You
Okay. Yeah.
There's only one more.
So this is related to the action of a 12 dimension, so you have a D12 acting on C2. Yeah. So D12, so the dihedral group with cardinality 12 is the same as the Weil group of G2. And the solutions to this equation, so they were written by Ekal, but well, among other places. Oh, it's better to write it. So this is the complete space of solutions, and you can find it in the works of Ekal. Hmm?
Maybe
No, but in this context.
You can certainly also find it, for instance, the paper covered in
Yeah.
me or in many other papers.
Yeah.
This is- the n equals 2 case is very easy.
Mm-hmm.
But now if you write it this way, I still can't see if it's the same space, but I think it isn't. But it's also isomorphic. I mean, by
Yeah.
so it's conjugate.
Yeah.
But I'm
By
not
linear
sure
transforms, yeah.
by fixed linear transform. No,
Yeah.
You can always apply some fixed matrix in GLN to your X.
Yeah.
And then you conjugate all of your G's by that thing, and you get an isomorphic space. And
Yeah.
This is certainly conjugate, but I think as it stands, it's.
Yeah.
So it might be helpful for the higher ones to do the same conjugation
Yeah.
Whatever you need to do for n equals 2, where it certainly will work,
Yeah.
then at least one space should be contained and the other visible, and then you have to show the equal. Because right now they just look different, so makes it hard.
So I can give you the formula for 3. So n equals 3.
But yeah, if you combine the two.
Yeah, you have p in 3 variables, which satisfy
It's clearly complicated.
this relation p of ABC equals of p of CBA plus two relations p of minus C minus A plus B plus C equals p of ACB, and you have 3 term relations p of A plus B plus p of ABC, sorry, plus p of A B plus C minus C plus p of B minus C A plus B plus C equals 0. So this set of relations.
But certainly also going to be the same. So
Yeah. So in fact, so the way to I compute these dimensions, I could relate it to the homology, the modular homology spaces of Grothendieck. So here, modular homology. And this modular homology is in turn related with, it's a model, if you want, for the homology of GL3. So that's why how I computed it, and I think that this I could not relate it exactly to the Grothendieck computation, but it's a very hard result here. The homology computation is the key ingredient is the same.
But they're not the relations of linear double shuffles.
no, they aren't.
In depth 3, they are.
No, they aren't exactly.
No, not exactly.
They aren't even in depth 2. They aren't. You have to make a substitution here. I've already found it's the matrix 1, 0, 1, 1 with some signs, and here also because in the double shuffle, for instance, the first relation is of course the same. Then there's a second double shuffle, which together with the first implies that P of ABC is P of CBA. So that part's the same. But then the other ones aren't the same because you can actually put in a fourth variable where they all correspond to 0, an extra cyclic symmetry. And so this A plus B plus C will be that fourth variable, and then you permute. So there'll be several changes to variables. One we certainly can't do it in our heads.
Yeah.
But there's definitely going to be a relation.
Yeah.
This would be very interesting. But then a simple universal linear relation, I think, between your space and the linear, but we should look at those two cases to see. And who knows what it will be.
So these are then formulas. I can give formulas in degree 4.
No, it's more than enough.
Okay. So now, how to construct this upper bound? So for this, one need to remember how the GRT, the algebra, is constructed. So GRT is a semi-direct product of GRT1 with degree, so degree 0, grading list of algebra. Okay. So yeah, and GRT1 is defined how? So GRT1 is a Lie subalgebra of what we call F2. So F2 is a free Lie algebra in variables x and y. So this is L of x, y of Z. So this, and there is a kernel map. So in fact, it was resolved by Enriquez that according to him, this is just the kernel of a certain map D going from F2 to the Lie algebra T4. T4 is a certain Lie algebra which is the algebra of infinitesimal braids in 4 strands. So T4 is the quotient of the free algebra generated by the Tij ij running from 1 to 4. Subject to relations, tji equals tij, tij tkl equals 0, and tij tik plus tjk equals 0. Here for three different indices, and here for 4 different indices. Hmm? Yes. Okay. Well, this is Lie algebra. Then we have a collection of morphisms, so Lie algebra morphisms from F2 to T4. So there exists so Lie algebra morphisms.
And what's the math?
Di.
Oh, you're saying, sorry, I didn't see that.
Yeah. So D sub I from F2 to T4, and they are uniquely defined by the images of generators. So and Di, so I goes from 0 to from 1 to 5, and you can give the list of images. So for example, so it's a little bit complicated. So one can write, for example, that D0 maps D1, let's say, map xy to T12, T23, and then D2 maps the same to let us say T12, T23, T24. D3 maps xy to T12 plus T13, T24 plus T34, and you have similar formula. Okay. And there are Lie algebra morphisms, and from them you construct a linear map. D, which is going to be the alternating sum, is a linear map from F2 to T4.
So can you renumber the Tij so it's completely symmetric? Can you put a variable 0 that you're ignoring so that you always have the same form as cyclic?
No, but it's using plane braids and not spherical braids. So
Yeah,
people, when you use spherical braids, it's more symmetric.
yeah, that's right. That's why the way he decoded.
So the label of the Lie algebras, you can't just introduce one extra variable or something to make it completely cyclically symmetric.
You can, but
You can
it's
do that.
spherical and it's
That's right.
it may be nicer looking, but
Yeah,
Okay, I mean, it also.
he does it in
Sure.
yeah, it's a
on the plane.
old, yeah, old-fashioned.
The plain old fashioned.
Yeah. So this is it. And this is a linear map. So the statement theorem by, so in fact, there is this GRT1 Lie algebra, was originally defined. So the Lie algebra was defined by Drinfeld as the intersection of kerm of D intersection the kernel of some other maps. And in fact, this is a result of Furusho, as I said, that in fact GRT1 is already equal to this kernel of D. Okay. So now we want to study the relation with depth filtration. An important fact And what he proved is that fact is that care of D is a Lie subalgebra of F2, but where F2 is equipped not with a standard bracket but with a Ihara bracket. Okay. So
so when you wrote the Freely algebra, you mean just with the usual bracket?
Yeah.
Ihara?
Yeah, you see, so it's a kernel. So these are morphisms for the Freely algebra bracket. Yeah, this is the algebra structure. But after you take this alternating sum, this is no longer a morphism for the Lie algebra structure.
Of course not. It's a sum of that. I understand.
Yeah. But the miracle is that this kernel is indeed a Lie algebra, but for another structure.
But it's not contained in the Lie, or is it contained in the Lie algebra spanned by x and y?
Yeah, this is F2. So F2 is a Lie.
No, but not for the ordinary bracket.
What? What was the question?
I mean, the Ihara bracket, as you wrote it, was defined on the
Lie of xy. Yeah. So I'm sorry, I have two notations for the same thing. So let us
So
say
it's the same as F2. So you're
yeah, it's the same as F2. Yeah. So F2 is a Lie algebra in two variables xy, and there we define the Ihara bracket with two brackets. Two different brackets, two Lie brackets. One is the standard bracket, Freely bracket, and the second is the Ihara bracket.
Maybe you could tell the definition.
Yeah, so you have Fg is bracket of Fg plus df of g minus dg of f, where df is a derivation which maps x to bracket fx and y to 0. So this bracket is what one should think is that there is a morphism from F2 with Ihara bracket to the derivations of F2, mapping f to d sub f.
Sure.
So this is just a Lie algebraic information here. Okay. So just to settle this thing, but actually we are not interested in Lie algebra today, so because this is just an upper bound of the vector space. So we don't use the Lie structure at all. So relation with depth filtration is what? So depth filtration in the case of F2, it's the following filtration. You have F2. It contains a Lie algebra Y. So by this I mean the ideal of F2 with a free Lie algebra bracket generated by Y. It contains again the bracket of this ideal with itself, etc. So this is a descending filtration, and this is the depth filtration. So this the F2 has let us say descending, so Lie algebra descending filtration associated to the ideal Y, and which is so this filtration, and which is the depth filtration. So the question is, what will be a filtration on T4 which will be compatible with this depth filtration in the map D?
Here you take a classical bracket.
Yeah, freely algebra.
Sorry, I know that who was Y here.
Why? So F2 has two generators.
Okay,
X and
it's
Y.
a generator.
Yeah. So what will be is the question is the statement is, so I consider the following ideal I. Let I be the ideal of T4 generated by okay. By T23, T24, T24. Then for each I, d sub I of y is contained in I. Therefore, d sub I of y, d of y is contained itself in y. Okay. More or less. Moreover, you have also di of bracket of y n times is contained in I bracket n times. And therefore, you have also that d of this y bracket n times is contained in I bracket n times. Okay.
Sorry, it's T2, 2, 3, 2, 4, 3, 4?
T2, 3, 2, 4, 3, 4. Yeah, everything except one.
Everything except one?
Hmm.
So
So
what,
this,
what are you doing? You're removing one strand, or
that's right. Yeah. You complete with respect to an ideal.
which is removing strand 1?
Mm-hmm. You can say that. Yeah. Okay. And from there follows that therefore
or symmetric ones. Just
There's a complaint.
yeah, but there's a slight complaint that for non-experts like me, since you didn't, not that you have to write all 5, but since you didn't write the complete thing,
yeah.
you didn't give the symmetric thing,
Yeah.
these I and J to us are just random indices, so 1, 2, 3, and 4 means nothing.
Okay, so
You can
I give you a
explain
picture. Okay,
The picture would help,
I give you a
yeah,
picture.
would help, I think.
So you have, in fact, F2, it's a very bad notation. F2, in fact, it will be written T3. And
I
Yeah.
see. Yeah, that already helps.
Ah.
I think from that I can already understand. If
Ah.
F2 is T3,
Ah.
I can imagine this picture. Okay, thank you.
Okay, listen.
So you're
So
referring
T3
to variable.
So, no, but for non-experts, I will explain. T3 is the same algebra as T2, with same relations, except that Ij go from 1 to 3, with the same relations, as T4. And you have a collection of maps, so it's like a kind of simplicial maps which go from T3 to T4, and they are defined as follows. So, in fact, you will say that Tij. So for any, let's say, for any map from 1, 3, let's see, from 1, 4 to 1, 3, which is partially defined. You associate to this for each map you construct, so call this phi. You construct a morphism from T3 to T4, x to x phi, And such a map you denote by the collection of preimages, in fact. Yeah. So, for example, you have, and so this map is defined as follows. So Tij goes to sum of Ti prime j prime, where I prime is in phi inverse of I, and j prime is in phi inverse of j. So this is a map. And so in fact, there is such an algebra morphism. And for example, so now in this notation, D1 is x mapped to x1, 2, 3, which means that the map phi is not defined on 4, so phi is 1 to 1, 2 to 2, 3 to 3, 4 is not defined. Then D2 is x maps to x1, 2, 3, 4, which means that the same, but 3 goes to 3, and 4 go to 3, etc. And then D3, x1, 2, 3, 4, D4, 1, 2, 3, 4, and D5 is 1, is 2, 3, 4. So this is it. So this is a part of the Greenfeld theory. So it's a linearization of the condition of associators.
You don't have to mention associations to do that.
Yeah.
Can you move if there's nothing to do with associations? It's just braids.
Well, in fact, this, well, the construction of this D, kernel of D is...
No, kernel of D, yes, but I mean these maps.
Maps, no. So it has to do with all this theory of associators.
Like strand doubling.
Strand doubling, exactly. So it's an infinitesimal version of strand doubling. So you have
So now surely
Tn is associated graded overlay of a pure braid group in n generators, and then you have morphisms from P3 to P4, collections of morphisms, and then which corresponds to strand doubling, and then the associated Lie algebra morphism are these ones. Okay.
So I mean, this does look now very cyclic, because if I had 5 indices,
Yeah.
then I could say the first one is 1, 2, 3, and then 4, 5
Yeah.
together.
Yeah.
The next is 1,
Yeah.
2, 3, 4, 5.
Yeah.
The next is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The last is 2, 3, 4, 5, 1.
Yeah.
On the back, and then it's completely symmetric.
Yeah.
Yes.
That's what I was asking, and then showed it the.
He
Yeah.
refuses to put them on the circle.
Yeah.
Yeah. Okay.
Stubbornly.
Yeah.
The question of circles. And,
But that's the way Hidekazu does it in his work. So.
yeah.
And in Arabic before. So.
Okay.
Okay. So. Okay. So in fact, what follows from this, the consequence of this, so no. So now we define
So what you're saying is y is T23 really.
why is T23 what?
Y, we can almost identify y
With
with
T23.
T23.
Ah, yeah, you're right.
And then you say that you can
Yeah.
either remove 2 or 3, and then you get T23, T24, T34, everything but 1.
Yeah, yeah. So well, first of all, the relation is that with this formalism here. So for example, how T3 is the same as F2. So T3, in fact, you can see that it is generated by T12, T13, T23. Modulo the relation of T12 plus T13 plus T23 is central. Okay? So it's a direct sum of F2 plus one-dimensional central algebra. And then the identification here is with xy go to t12 t3. So that's an explanation for this complicated map structure. A full explanation. Okay, so now we have a descending filtration on T4. T4 contains bracket I, bracket contains cube bracket, and it turns out that you have a map that D maps Y bracket n times to I bracket n times. Therefore, you get an associate graded to D. Then you get a map Grothendieck, which goes to Grothendieck with respect to the filtration, so depth filtration is 2, to Grothendieck with respect to filtration by I of T4. So the point is that the program is we compute to compute and then what can show, so it is easy to show that if you take Grothendieck of GRT1 is contained in the kernel of this Grothendieck, of this map from Grothendieck Y of 2 to Grothendieck I of T4. So this we call, so this for any I, for any depth I, and that's what we call the upper bound space number I. So in fact, this is an upper bound space, but then we need to compute. So the program is first to compute this Lie algebra, and then this map.
Do you have a semi-direct product? T4 is T4 the semi-direct product of I and T1 to T13 or something?
Yeah, well, T4 itself, no. But in the Greux, yeah. But because the 0 degree component, the Greux is graded, so the 0 degree component will act on the other one. So, program. First point is to compute Grothendieck I of T, and second is compute the upper bound. So it turns out that one can compute this Lie algebra. So Grothendieck of T4 is a Lie algebra you can explicitly compute. And here is a presentation. So there are two results on this. First, there is a presentation as a Lie algebra. And the second is we have a basis. So basis for each degree component. So I just I explained this result. So we need to introduce some rings. So we call R sub A. So we take three commutative variables, U, V, W, the commutative variables. And then we define some rings. So R will be the Q of UVW over U plus V plus W. R sub A is, so it's basically polynomials in two variables, in U, V plus W. And then you define RB and RC by cyclic permutation. So these are three rings. And then you present the following algebra. So, G, so define G to be the algebra presented by. So you have three types of generators, so it will be graded. So generators in degree 0. So in degree 0, you have U underline, V underline, W underline. In degree 1, you will have the A of R sub A, B of R sub B, C of R sub C, where RA belongs to capital RA, etc. In degree 2, you will have phi of R, where R belongs to R. Plus,
So what do you do by A bracket RA? For each element RA in capital RA,
you get a generator, which we
D'accord, okay.
collection of generators. So just you don't write they are indexed by elements of the ring. Okay, and relations. You have U bracket with A of so X A of Ri is equal to U of A of U times Ri. So the bracket with an element here of one of the generators of degree 0 works the same way as multiplying by an element the commutative algebra. Yeah, and the same
That's defined the bracket.
for B, C.
What is the definition of the bracket? This is
Relations. So freely algebra
okay.
modulo this relation.
Okay.
No? Same for B, C, and phi. That's one thing. The second thing is that you have relations like A over A, B over B is equals to phi of some map FAB of RA times RB, where FAB is a map from RA times RB to R, which under suitable identifications goes to this RA is a polynomials in one variable. This, let us say alpha. This RB is polynomials in one variable, let's say beta. And this is polynomials in two variables, alpha, beta. And this will just be multiplication. And plus cyclic relations. Okay. So the statement is that so this is B graded. By grading. So you would say, so you have depth degree and weight degree.
Did you ask the relation of the, say, the generators A of AR, A should be linear,
Yeah, of course, yeah.
and maybe also what is A of R prime A? Is it just when you multiply two polynomials in RR, what is the corresponding is the relation with doing something for A?
Wait, AA do you mean or what?
So
There is no AA relation.
you have two polynomials in RA,
Yeah,
P and Q.
yeah,
So you have two generators,
yeah. A of R, A of P and A of Q.
Q. And is there a relation between those two and A of P times Q?
No. Just additive, but it's not multiplicative, so you don't know. Okay. So this is a bi-graded Lie algebra. So you have, let's say, the degree, so we say weight, and depth.
So where do you use the ring structure? Where do you use the ring structure?
Here. So you use an identification of RA, which C of alpha, which is a ring, in fact, identification. Yeah. And here also. And here this, and also this is a ring identification, and this multiplication uses the ring structure. Okay, so weight, you will say that a degree of U is 1, and then degree of A of R is degree of R plus 1, and degree of phi of R, or array, will be degree of R plus 2. And this depth filtration for which degree of U is 0, degree of A of R is 1, and degree of phi of R is 2. Those are two gradings. Okay. Then the statement is that this Lie algebra is isomorphic to Gre I of T4. By the way, so Gre sub I of T4 is also bi-graded. Because in fact, this is a direct sum of Gre I sub I of T4, which is itself the bracket of I times, over the bracket of I plus 1 times. So we will say that this is a part of weight I. And as for the degree, in fact T4 has a degree. So we would, sorry, the depth one. And T4 has a weight degree for which each Tij has weight 1. Weight of T12, Tij equals 1 for any I. And in fact, I is homogeneous for this degree. Therefore, Gre sub I of T4 inherits the weight degree. So all this shows that Gre sub I of T4 is bi-graded. So the statement is that there exists a unique bi-graded Lie algebra isomorphism from G to Gre sub I of T4. And it is given by the following formulas. So you take U V W to the class of T12, class of T13, class of T14, which lie in the knot of T4. Then you take A bracket V to the n. So take the classes V to the n is a well-defined element in R sub A. You will take this to add of T12 to the n, T23, and plus cyclic permutation in UVW and 234 in ABC, UVW and 234. So individually goes this way. And finally, if you take phi of u to the p, v to the q, this maps to the class. So all this in it's a class in Gr1 sub I of T4. And this is going to go to add of T12 to the p, add of T13 to the q, apply to bracket T23, T34, and the class of all this in Gr sub I to the 2 of T4. So, for example, well, and there is a, so this can be proved. And there is another theorem which gives an explicit basis for this Lie algebra. In fact, these two theorems are proved at the same time, in fact. Basis. For these two isomorphic Lie algebras. So in fact, we will construct a collection of vector spaces. So we will 4 vector spaces, A, B, C, and X, and plus linear morphisms, linear maps, from A, B, C to X to G, and they induce Lie algebra morphisms, Lie algebra morphisms, from the free Lie algebra over each space to G. And the statement will be that the direct sum of these linear maps is a B-graded isomorphism. So all these spaces are also B-graded. So here are the details. So you take A to be some vector of alpha n, where n greater than 0. B, it will be a vector of beta n. C is the same with gamma n. And here, alpha of n has weight 1, and sorry, depth 1, and weight n plus 1. Here also and here also. And the third space is a vect of a collection phi of, you take indices n1 and k, m1, ml, pq, where these numbers k, l are greater than 0, the ni, mi are greater than 0, and the pq are greater than 0. And this has depth k plus l plus 2, and degree and weight n1, so sum of n's, sum of m's, n plus 2. And I just need to specify the linear maps. So alpha n goes to a of vn, plus cyclic permutation. And this phi, this big phi, goes to product of adjointation. So add of, I'm sorry, add of v n1, add of v a of v nk, and then you take the product of add of b m1 w, add of b w ml, and then phi of pq. So to establish this, you need to compute generating series. But this works.
But can you give an idea?
Hmm?
Can you give an idea of how you prove the first part?
You prove the both parts at the same time. So the morphism is clear. So why you have the morphism is clear. Because these relations, for example, why you should quotient by u plus v plus w. So it's because you have the relation t12 plus t13 plus t14, bracket with t23, t24, t34 equals 0, for example. So it's natural to do it. Well, so why you have a morphism is rather clear. Why this relation holds is clear also. Then you need to compute to prove that you have a surjective morphism from this to this. And what you do is you compute this map to x to g and to T4, so to graph of T4. And it's easy to prove that it's surjective. And then you need to compute characters here and there and prove that they are the same. And that's it. And you need to prove that this is surjective. This is it. Plus character computation. So that's the idea of the proof.
Where's the
Character of the sorry, character graded dimensions. Big graded dimensions. Character of
Oh, yeah.
you have an action of the square of the multiplicative group. So it's a percentage of that in which Tanaka category. This one.
Where's the unicity of the morphism is coming into the picture?
Hmm?
In the theorem
Uniqueness.
where the unit degraded isomorphism, why it is unique and where it's standing?
Sorry. There is a unique degraded algebra. So the point is that there is a morphism. To prove that there is a unique morphism sending a mapping generator to particular elements, and this is it. The statement is that this is an isomorphism. This is absolutely, this is the main, well, difficult. Yeah.
But you could imagine that they were different. Is
No,
it
because once you define the images of generators, you know the images of everything. Understand? So if you have an algebra which is generated by something,
the statement is not that between G and with I, it's
Yeah.
just one
Such
I.
as- such that.
It's
There's
that,
a
that,
that.
blah, blah, blah.
Yeah.
Let's stop.
okay. So okay. So basically this is it. And then now how do we compute? So this really is the first part of the program to compute this. Then we need to compute this upper space, this upper bound. Yeah? So upper bound was the kernel of Grothendieck. So we need to compute Grothendieck. So here, in fact, to compute Grothendieck, so one have to compute each of the greux of the i's and to sum them up. And what one obtains is, in fact, that you don't map to this L of a's and b's and c's. You just go to this L of x. So fact that in general, Grothendieck maps so greux y of f2 to in fact so greux I of t4, which is isomorphic by this theorem to LA plus LX, but in fact it maps just inside LX, so there is a map to L of x mapping here. So in fact, you just need to compute this kernel of this map. The second thing is that you want to represent explicitly this greux sub y of f2. So, so for each i, greux I of y of f2 is isomorphic to a space of polynomials in x1, xn. So how does this work? In fact, you can think about it the following way. So you can say that greux y of f2 is the same as the algebra f2 minus cx, tx. So you take away the x, and because you don't look at depth 0, so depth greater than 1. And then by another elimination, this is a 3D algebra in y, xy, x squared y, etc. So it's a double bracket. So variables which you call xi of n, the set xi of n is addex to the n applied to y. So this will be L of xi of 0, etc. And this is, maybe you will say this is inside the tensor algebra, or maybe you will say that this corresponds, you don't need the xi, you say that x to the n y, you let it correspond to x to the n monomial. So this gets in bijection with 3D algebra over the algebra in one variable, yeah, which is itself a subspace of the tensor algebra of Q of X. And this is the direct sum of Q of X1, Xi. And in fact, you will see that here, the Grothendieck precisely maps to this space. Well, when you do this, you find that this is the same as the Ma construction of Ecal. This is also Ma on F. Ma. So, so this is it. So when you use this isomorphism to express Grothendieck, so Grothendieck, you can compose with the isomorphism. So you get from Q of X1, Xi. So in fact, no. So you say that in fact you can express conditions under which conditions? Condition for P here to correspond to a Lie element. And furthermore, you can express, so you can show that you have this map Gre of F2, Grothendieck to Grothendieck of T4. And this this embeds into polynomials in I variable. So it turns out that you can show that in fact you map here by co-restriction into L of X. Yeah. And in fact, you can show that of a fixed weight, of fixed depth. Or then you can show that this space, this space of fixed depth is isomorphic to a direct sum of several copies, donc a certain direct sum of Q of X1, Xi. And it turns out that you can extend the map this way. And the map defined here is just defined the way. So this is for weights I equals 2, 3, 4. No, conjecturally for every, but up to now 2, 3, 4. And that therefore you can express Grothendieck. So here and the maps here are of the form each map alpha. So each map alpha has the form takes P to sum of C alpha I, C alpha G, G of P, where G belongs to GL sub I of G. So that's why you get this description of the upper bound space. So that's what. So putting everything together, it goes that up sub I is the space of polynomials P in Q of X1, Xi, such that they satisfy Lie conditions, and it also satisfies that for each alpha, sum of C alpha G G applied to P equals 0. From which one derived? So in degree 2. So so when one gets space, so conditions which express as the action of the right group of G2, and we get exactly, so can compute up to. In degree 3, we get a double shuffle space which relates, so when some space related to the modular homology of Goncharov. And therefore, and then to the cohomology of GS3. And from this, you can compute the dimension. The dimension of the upper space in degree 3. And in degree 4, up to now, we have only just this formula and no precise investigation of the size of the space. So this is it.
Thank you very much.
Any question?
So you have a cyclotomic version of GRT, right?
Yeah.
So your program,
Yeah,
your argument can also extend to this cyclotomic.
Yes, but
That's
this,
when
this I did not try
Homework.
to do. This I did not try to do yet. Well, yeah, it's an interesting project. Yes. But
You're invited to Strasbourg.
yeah, it's a good subject. Yeah.
Where exactly do you lose information? I mean, it's an upper bound, it's not.
Yeah.
So
Well,
where exactly it's because?
but each time you have a map and you have an associated gradient, then you
Yeah, in principle I understand, but here
it's a question of spectral sequence.
it's a question of spectrum. Yeah,
Yeah.
it's something. Yeah.
Yeah, because you can.
But for this specific map, there's D. I mean, there's kernel P.
Yeah, yeah. Well, it's always the same. So you
For
have
instance, maybe.
so you have the filtration. Yeah, you the space A, the space B, and then you have Fi, Fi plus 1, Fi, Fi, I plus 1, Fi plus 1. So you have something in the kernel which lies in Fi. So it gives you something in the kernel of the associated gradient, but you can have something in the kernel of the associated gradient which, by malchance, goes there. Yeah.
By malchance.
By
By bad luck.
unfortunately.
By failure of luck.
But maybe it would be nice to write down the spectral sequence and see.
Yeah, but
we can
before
prove
that,
something about
yeah, but before that, you know, the spectral sequence goes from this kernel for this gradient to that gradient. So
Yeah.
for the kernel of this gradient to this gradient. So you first compute the kernel of the gradient,
Yeah.
and after this is done, then yes, you compute the
You
spectral
compute
sequence.
the E1 term.
Yeah.
Some
Yeah.
E1 term.
Yeah, but you need to first compute the kernel.
Yeah.
Which is well, what issue?
Any other question? Okay, let's close this.